Okay, so I'm very pleased to introduce the next speaker, who is Professor Gang's son, and he's a professor in the Department of Biological and Agricultural Engineering here at UC Davis, and he researches the development of novel antibacterial materials for biological protections, including medical and chemical protective clothing and food safety products. His group has developed chlorine rechargeable, daylight-induced, photoactive biocidal materials for water disinfection, biological protective textiles, and fresh produce disinfections. He received a career award from the U.S. National Science Foundation in 1997 and the Alney Medal in 2016. We're very pleased to have Professor Gang here and look forward to your presentation.
Thanks for the introduction, and also thanks for the invitation to speak here.
I need to give.
Maybe I can speak
No,
now.
this one's for the online people.
I see. Yes, okay. I'm thinking we have the double duty. Okay. Again, and thanks for the invitation, and also thanks for the opportunity to speak here. And in fact, I have never worked in the food package, particularly for the produce. But in recent years, I worked with Professor Nitin here and on certain of the food safety related products. But we have done a lot of work on the polymers. When I received the invitation from Irvine, so I actually spent a lot of time. And also with the help from Beth, and particularly with some of the early versions of her presentation, it provided me a lot of clues on the packaging materials, the special requirements. So with the requirements and the desire on the biodegradable materials, alternatives to be used for the packaging materials, and also I try to see that I provided a little bit brief introduction. Now, obviously, there's a huge concern in the climate change and also the environment, microplastic, plastics, and in the ocean, and so I think that the pressure to change to the biodegradable to make our society and the environment more sustainable is becoming the trend. So I do see there's huge potential for the use of the biodegradable materials. But here, I also want to just make some kind of clear definitions of these materials. So first, the plastics are made of these polymers. So polymers are large molecules, and so we actually basically we describe it as a manufactured polymers and materials. And we have two sources. One is actually naturally produced, or another one would be man-made. So we have a lot of, basically now the used ones and the commonly used ones would be the man-made ones. So you probably call it the synthetic and or petroleum based. But in fact, man-made ones could include the petroleum based and also naturally based as well. So knowing those, we also would look like what are the name of the biopolymers, because the biopolymers are representatives of so-called biodegradable. And well, let's say biopolymers may not be fully in some of them, but let's see if we define those, if we define the biopolymers as natural polymers made by nature, and those are all biodegradables. That include actually here would be that, so the definition would be polymers produced by the cells of the living organisms. So including starch, everyone is familiar with the starch, cellulose, proteins, lignin, hemicellulose, and nowadays, this is the polyhydroxyalkanoate, which is a new polymer. Nowadays, it's very popular. It's bio-based, and also we also should name it as a biopolymer because it's produced by microorganisms. Okay, so now you probably see there's some kind of overlap because the people also call this as a bio-based. Anyway, now I move into a bio-based. So bio-based, we define them as obviously come from the biomaterials that could come and in different ways. Either and you come from the large molecules, which is the biopolymers itself, by doing some kind of, we call the chemical modification. And so you do see there are modified starch, there are modified cellulose, there are modified proteins nowadays also get into the market and serving as biodegradable. Later on, I also will say more specifically on the biodegradable. And also now we have the so-called bio-based polymers actually come from some use of the monomers. The monomers are coming from the bio-based materials such as the starch, the glucose actually trace back. The good representative would be the polylactic acid, which is the PLA. And if you want to see, there's also more man-made bio-based polymers. And one example is a bio-PE. I don't know how many of you heard about PE. Bio-PE is similar to our polyethylene, widely used as a packaging material, but it comes from the bioresource. This is made in Brazil, okay? And they're using sugarcane and hydrolyze it into the glucose. And from glucose, obviously, can ferment it into ethanol. From ethanol, they can dehydrate it and produce ethylene. And the ethylene actually comes to the same monomer as the petroleum-based ethylene. So they claim this is the polyethylene, so with the abbreviation of bio-PE. There are many other related bio-PEs. So based on the name of the bio-based polymers, we do have a huge inclusion. But whether those polymers are biodegradable, questionable, because some of them are biodegradable, particularly those nature-produced polymers, they are biodegradable, no question. But for those bio-PE, there's no any kind of difference in the structure, in the performance, except that the manufacturing process uses the bioresources, okay? And so we do. So now I have to say that I will use a later version and to redefine the biodegradable and also compostable and so on. So we just try to define this. Biodegradables, normally we would define them as we can break down these polymers and after the usage into the gases, carbon dioxide, water, and others. And in fact, if we really break down all these things, there's overlap with the so-called compostable. Okay, so there's some kind of overlap, biodegradable and compostable. So you'll see a little bit more clearly. And also, I will try to learn the packaging film. And in the past few days, after reading Beth the presentations she sent me, and also try to find related materials about the specific requirements for the packaging film. So I found on something based on my understanding. I hope you here, the audience, are more expert in the produced packaging. So I thought one is obviously the transparency, which is optic effect. So we do look for how clearly we can see the product through these packaging materials, and we actually the transparency is mostly determined by the polymer's structure, which is what we call the crystal structure. If there's more crystalline, and in fact the film becomes stronger, but it actually becomes cloudy, and so you lose the transparency. So if you want to maintain the transparency, we have to keep the polymer in the so-called amorphous. Amorphous is just like a glass. If the polymer becomes crystal, crystal becomes cloudy and opaque. So transparent, just like a glass. A glass is 100% amorphous. But if it becomes amorphous, there's also issue that are actually related to the tensile properties. So the tensile strength and also the elongation. Amorphous is less stable, less strong than crystal. Also, thermal properties, actually, that's determined by the polymer structure itself. All our natural polymers are good and in general, but they do not melt. Most of them do not melt. So you have to find, if you want to process and utilize them to make it into other, particularly into the film structures, you have to find a solvent. Or otherwise, you have to chemically modify to make them we call the thermoplastic-like. So meltable is called a thermoplastic. You can treat it. Anyway, another important issue I found is Beth just mentioned earlier is oxygen transmission rate. And there's more gas barrier properties in the oxygen, the carbon dioxide, and also maybe ethylene. And there's even also the next one would be moisture and the vapor. And sometimes people also concerns when we use natural polymers, particularly bio-based materials, and many of them may have a solubility issue. And even though they are not solid, 100% soluble, but they could swell, they could change some of the properties once they're exposed to water. Okay, so I also want to briefly mention some of the most common polymers and they used nowadays, and I learned, and also, and most pictures just come from the internet. So the most popular one and very inexpensive, very affordable would be the polyethylene. Polyethylene has different varieties, high density, stronger, okay, and the low density, much more stretchable, and linear low density, it's even more flexible. And so they all bear the feature that it's soft, flexible, and stretchable in something, except that the HDPE may be able to provide a little bit more strength. We also have other polymers and widely used as other, such as ethylene vinyl acetate, commonly named as EVA. But this is the polymer not singly used, but it's also flexible, tough, and miscible with polyethylene. So nowadays you see a lot of mixing, multi-layering using the EVA because the EVA has very good performance in serving as oxygen barrier. Also, we have others, and like UVOH, which is vinyl alcohol called ethylene, and those are the two. They are similar, but the UVA has higher ethylene content, so it has a very good miscibility with the polyethylene. But once you go to the UVOH, it provides even better barrier function, but it does not have any miscibility with the polyethylene, which is a common commodity packaging material. Polypropylene. We all know polypropylene. We use a lot of polypropylene. And mostly you see this, the boxes and the containers made by the polypropylene. But polypropylene can also be made into the films. But a little bit stronger, it's good barrier to moisture. And in fact, all the polyethylene, all we call the olefin polymers are good barrier to the moisture because they are super hydrophobic. We call hydrophobic. Once you go to UVOH, it becomes hydrophilic. So it's different in the performance. Okay, there are a little bit more other, and I don't know how often this polystyrene film. We do use polystyrene. We have the styrofoam box. Those are outdated. We do have a lot of clear, transparent, and the polystyrene materials because it has some kind of advantage. It's printable. You can print the figures on the polystyrene directly. Actually, I forgot to mention the EVA and the EVOH also have the nature that can be printed as well. And also, PVC, I think everyone knows, we all use which is the food wrap and widely used as a packaging material, but has a very unique property which is clean, and you wrap it, stick onto it, and also stretchable. And we also have other allow this similar product. Good representative would be the PVDC. This one, not singly used, I found out that this is mostly served as a coating additional layers, adding to other polymers, because this has a good barrier to most of the gases. So if you really want to increase the barrier functions to block all these the different gases, that would be the polymer needed. So with those said, including a few others, and PVOH, and I use the color code. Once you see the green, it means biodegradable. And this is the only polymer that defined as biodegradable, although it's purely petroleum based. purely petroleum-based, but it's biodegradable. This is actually water-soluble as well, and a very high molecular weight may not be. But most of the common products is our detergent pots. It's not, I don't know how often used for our food produce. That we do see this detergent pot, which is the one that they throw in the washer and dissolves, and that's the polymer. Okay. And also we have the polyesters, the common one. Polyester is used for our water bottle, but also used for film. It's very clear, transparent, good barrier, good thing, but a little bit more expensive maybe than the others. A little bit rigid, stiffer, and stronger. And also, more often you see the nylon. I don't know how often nylon is used for produce, but it's a strong and very useful and packaging material, and based on this literature. Anyway, so now I'll switch to biopolymers that can be used for packaging materials. So I try to group them into based on the naturally based polymers. So we have first starch, which is a very common one. Okay, starch-based. Starch-based one, it's also has been used as a packaging materials. Mostly they claim this film, this package would be edible. So you can eat the the object, you could eat the container as well. But we do have other very interesting, they call the thermoplastic starch, and those would have other additional functions, serving as additional layer, mixing with the other. But this bears the function, bears the property as biodegradable. Also, second one, actually, this is the more common, serving as a packaging material for produce for many other food contents, cellulose based. And the famous one would be the cellophane. Cellophane is a regenerated cellulose. A traditional way to make cellophane might be more environmentally polluting, but nowadays I heard they're using different processes, maybe more environmentally friendly, because of the traditional cellophane production uses uses carbon disulfide and other water pollutant, air pollutant, but it's an older story. But they do have a lot of, the cellophane has a lot of other advantages. It's also, with the different variety, particularly coated. If you look at the category, they are coated with the nitrocellulose, coated with the PVDC, with the increased barrier functions for different food products. Disadvantage is cellophane is more rigid, not so soft, and does not have the self-cleaning, not stretchable. So cellophane's use would be limited by such a kind of property. Proteins, and proteins have been developed. In fact, food science department, 20 years ago, there was use of using whey proteins serving as films. But I don't know whether there's any product. I didn't see the product. But more recently, USDA and also use this casein milk protein and to develop the film. But now you see it's transparent, it's flexible, and obviously this would be fully biodegradable. The major issue would be the end, would be cost, how much would it be? But this goes to the biodegradable areas. So I show you some kind of examples, and it's all brought out from the internet. And nowadays, actually, one of these products is purely biopolymer, close to the market, widely have a huge potential for our produced packaging material, probably would be the PHA type of this. And the prices are dropping, and also with the different varieties. So I will have this slides to make this introduction. So, and when you see this is the produced by microorganisms. So this becomes more sustainable. You can feed the microbes with the glucose. And the glucose is obviously abundant, come from cellulose, from starch, from everywhere. And then you can produce all different species of the PHA. PHAs represents a group of the polymers. I'll show you some of these. But anyway, they put them in the group because they belong to the same type of the structure as aliphatic polyester. And so you see here is a lot of potential applications for the PHA. And as long as the price dropping into a kind of even more affordable range, I think that you probably will see more products in the areas. So here I know it's a very cloudy, not very clear, but I do have a source to show you where these come from, and if anyone is interested. And also, bio-based polymers that actually come from mostly the monomers from the resource, from natural resource. Most representative would be the polylactic acid, the PLA. I'm sure everyone already heard it. It's most popular and already reached into the market, and with all different variations, the product. It can be used into a kind of a hard packaging material, rigid, and also can be made into films. Nowadays, the films are made in the blended compound and with other different species. And so this is close to our real world for the packaging material. And again, when I use the green color, it means it's biodegradable. Later on, we also will redefine the biodegradable and about or the compostable terms. Okay, and there are other different varieties of the bio-based materials. And those are not biodegradable because once they are made, it's almost the same as our synthetic polymers. But one of these is very interesting. I don't know how many of you that to see. We have a bio-PET. Bio-PET is the same thing as a water bottle. But there's also a real better bio-based polymer, which is called the PEF. It's called polyethylene phenolate. And it comes in a little bit slide structure because the PET, the T represents the benzene ring, but here it becomes the furan. And the furan come from our glucose. And those already become the replacement of your future bottle. And the Coca-Cola already signed the exclusive license, right? And try to use the PEF. Obviously, there would be probably it would be something and in the future to see this is the real bottle come from the PEF and packaging materials and others, but I have not seen its biodegradability and starting. So, but obviously recyclable as similar as the PET, our current bottle, but those are the good ones that really represent the future of the bio-based polymers. So now, I also want to really redefine those biodegradable polymers with those names and learned. So biodegradable polymers, so mostly when we see biodegradable, and anything is degradable, degradable means the polymers are already losing some of the original properties during the under certain conditions. So biodegradable, it means that under the natural conditions, under microorganism reactions. And so here is a biodegradable base defined on top of this degradable. But later on, people try to see the compostable. So I try to search what would be the difference of this compostable versus the biodegradable. So I highlighted that the compostable actually is still within the biodegradable. There's not much clear difference based on my understanding. Compostable polymers, minimalization and no any kind of a negative impact to the environment. So which means biodegradable polymer, even they go about biodegradation, it might still have some kind of a degraded products having some kind of negative environmental impact, even though they're degraded. So that might be the only difference there. So compostable and biodegradable. Okay, so biodegradable polymers, so I want to try to make sure that we have all this included. All these natural polymers, including those, some of the bio-based polymer, the PLA and PHA and others, those are all can be defined as biodegradable polymers. And also we do have additional, I did not mention, that in this introduction that there are some other biodegradable polymers, mainly produced by the petroleum chemical. And that includes some of these names is very not very common, used in the produced packaging material. But gradually you're going to see, because they are with the nature of the biodegradable and also with the nature of the coming from the petroleum chemicals, it brings in the cost down and brings in the nice image. And so those actually are blended with our other biodegradable polymers more often and to produce different products. So those polymers include these aliphatic polyesters and the PEA, PBST, and the PBAT. And I do not want to go into all the chemicals names, and we do have this and included in the later part. But also, again, all the polymers used for packaging material must possess the right properties. So I found some kind of table and also added the enriched. Again, I also used the color code to tell you that those belong to the biodegradable polymers. So that are the important properties that might be meaningful to you to understand. So some of them, so the PBAT maybe still should be the green color, I forgot to. Anyway, so look at here, we do have these issues. Tensile strength means how strong the polymer, if we make it into the film, to survive the stretch. And also the modulus actually shows the resistance, how rigid, how stiff it is. And also elongation shows how much you will be able to stretch them in the stretchability. And just give you a kind of a simple comparison, we will see this. The common LDPE, which is low density polyethylene, is much more stretchable. So you probably can stretch 10 times. 100% would be one time, and also 1,000 times would be 10 times longer. Okay, but they do survive pretty good strength, and so it provided pretty good strength. But if you look at the PLA obviously would not be so stretchable. Okay, it's pretty strong, but not so stretchable compared to others. So look at those things, at least you find out that some of these useful properties. The second one actually is that there are the barrier properties. So I try to find more of these, and because Beth asked me to see these special properties come from the alternative polymers, I also want to see what are the current packaging materials. And I found out, well, here, and the OTR, actually high represents the oxygen transmission rate high, low would be lower, and obviously you see this in some of the ranging from very high from low. But also I want to tell you that I did not find the thickness related issue. Pretend this is all same thicknesses for the same package, but this is all come from the source as a film, multi-layer films. Okay. Also, I try to find the more relevant data, particularly using the same unit of the OTR. And I'm not good in converting all the different, because each one is, there's almost over 10 different units for measuring the OTR. It's confusing. But finally, I converted them and spent some time, and I found out most of our natural polymer, or bio-based polymers, have very low OTR. So they are serving all the good barrier. And there's actually a general principle for those with the polar structures, very strong polar structure, they are able to block this oxygen transmission through the films. So now you see, we do have a comparison, and also based on the mechanical properties, we do see there are some kind of good or some kind of weakness of our natural bio-based polymers. But also on the other side, as a material scientist, I also try to see that the polymers can be blended. But it's depending on the miscibility of the polymers, because the blend could provide you good or bad properties. So I use a synergistic and also non-synergistic or additive. Okay, so some of the polymer blends provide you the additive, and which is just so we can predict the property of your blend. And that actually significantly drop your the cost, so brings in the economic value, also without losing the function. But if it's synergistic, even better, because mixing and really provides very interesting phenomena, and also economic and also other performance to the polymers, which is the reason nowadays you see a lot of films made in this. And also, in order to overcome the weakness or enhance the advantage, people are using multi-layer films. Nowadays, take any kind of single film for the package material. For produce, I'm not sure how how well, but I do see a lot of food package, because we happened to work with one of the company and making this Oreo package. I just realized the Oreo package, this cookies, is so thin you can tear it off. Contains 3 layers, such a thing, and printed, and it comes with the high HDPE and the EVA, and because we try to create antiviral functions for this. Anyway, so with this, polymers must be able to make into multi-layers that would be adhesion functions, requirements. So good thing is, as I said, you probably will see in multi-layer materials, a lot of time they use EVA, because EVA has a good adhesive functions with polyethylene, polypropylene. So the good means good, okay? And so those are the most common and cheaper packaging material. This is the very interesting. There are some kind of other stuff, but I think the reason I modified the slides here and try to show you something, and indicating that why they vary these structures, because they do have, and the EVA would be a good one. In fact, I want to draw the EVA as a medium layer, and I didn't have I should make sure that actually LDPE and the HDPE should be outside the layers. EVA would be the middle layer, because EVA, there's a printable, but it doesn't matter. Okay, you just see those are the things. Miscible means that you can make a homogeneous polymer. And actually, this is the edit. We found it's very miscible with the LDPE and the HDPE, that the EVA. We did it in our lab, and very interesting, transparent, comes no economic negative impact. That actually lowered the cost of the EVA use. So obviously, the increase is different other performance, although we did not measure the OTR, or water vapor transmission rate. But also, multi-layer, I found that there are a lot of interesting, and possibly this could be the food or the produce. So you see a lot of these uses multi-layers of their own. So you have a LDPE and HDPE, LDPE multi-layer. When they let it, because the HDPE provides the strength, and the LDPE provides the stretchability, but they are the same thing, so they have a good self-adhesion functions. And there are others. If they don't have the good self-adhesion functions, nowadays the industry have the very quick so-called plasma treatment, and multi-layer, one surface or 2 surfaces, they can increase the adhesion. So natural adhesive function doesn't represent. In old days, meaning very important. Nowadays, it becomes less important. They do have one quick process, plasma treatment, to improve all the adhesive functions. Also, I try to find more multi-layer from the bio-based materials. And this comes from the patent, because nowadays there's more kind of a proprietary information for these multi-layer. So this is come from the PLA. So you have a layer A, and then also you have a layer 2 with a different. The common thing is here. You see PLA, PBAT. Remember I said the PBAT is it's a biodegradable degradable polymer, but it's come from the petroleum base. Okay, that can be produced in lower cost. Obviously, brings in other functions that the pure PLA may not have. So anyway, so overall, you will see such. Even more interesting part is the look part is there. There are some commercial products is a PLA, and also with the starch. Okay, starch based. Okay, and starch and the PLA, but remember the starch is very hydrophilic, and the hydrophilic ones and normally absorbs the moisture a lot. So I think there would be some kind of indication that they use the starch layer to provide some kind of balance for the moisture for the packaging materials. Okay, this comes from the picture I got from Beth as well, and I try to learn and to see, but I do see, and based on whichever we introduced from these the materials, I see a high potential of using those biodegradable polymers, such as the PHA and also PHA and the PLA and stuff. Maybe one single polymer may not be able to fully reach this the PE or PP type of the materials, but multi-layer probably can provide a very good one, including the hard stuff, but not for this type of the totes and the big carrier stuff. And this probably is more reusable and still made. But I think in the long run, PLA may be able to replace those. Again, I try to also understand the packaging materials of fundamental requirements. As Beth already mentioned, there are reduced perspiration and control the ripening, and also reduce damage. The damage would be microbial damage or other damage. And in fact, from next speaker's talk, you probably see, I think the packaging material could bring in the functions, and particularly with the function that reduce the microorganisms growth and others. But also you see that the barrier property really controls, and very interesting that if you really can regulate the OTR, oxygen content in the container also, and limit the production of the carbon dioxide by the produce. So that actually have a huge impact. And also in the years, recently we also worked in the temperature control. We hope that we can cool, and we made this and non-meltable ice. Hopefully there would be some kind of application for our packaging material as well. And and you can reuse and non-meltable, and also but the material itself is biodegradable. It's produced by a protein. So again, I see the multi-layer and also the biodegradable polymers are able to reach some of these requirements for the produce industry. And so there could be a way that you miss or multi-layer or others. But overall, the issue would be the cost, and I will also show you in the next slides. I try to find the cost-related issue to give you a kind of a picture. So I think the multi-layer is not the issue for achieving any kind of requirements, because optical property multi-layer definitely can provide, and even with all those advantages, except that there's the cost. And another concern comes from multi-layer is you have to select all the materials biodegradable in order to still make sure the overall multi-layer package would be a biodegradable material. Otherwise, there's other issue even for the recycling, for reuse, because it's hard to separate. And this is the one from a more recent study. They show, well, there's a lot of new bio-based material, and for package, huge interest. And it shows you the commercial-based, still the plastics, but there's also some of the plastics come from these different materials. Well, large stage would be the PLA. Now we know the PLA, and also I said that the PHA and as well. So increasingly, you're going to see a lot of other and more. And on the top, you probably see the bio-PP and also bio-PE. Those are the very interesting ones, but they are not representing the biodegradable. It's a bio-based. And there are also the current stage of productions of these different bio-based materials, including this is the very little bio-based, the PP, and also the bio-PE actually getting pretty high. This is the only made by Brazil, one company, and with this claim, it's also accepted by the industry. The international users. Okay. PHA is still at a slow, even though I said that there's more, but you also will see PLA is the most compatible, and starch still in the area, and mostly it's modified thermoplastic starch that's used for different packaging. I'm sure it's probably not used for produce. So I also want to try to see whether we can find the related information, because the cost is the issue. So now you see this is from the based on the number the European Unions, and 2016. It's a little bit old, but I think it's still meaningful to us. So those are the polymers. So if you look at the cellulose acetate is a bio-based material, but it's not biodegradable. But PLA prices, they actually listed in pound, the US pound, not dollar, but it doesn't matter. The unit is not meaningful here. We just see the numbers. And the PHA is in the 5, but if you go down those common polymers, it's way cheaper. Okay, so that actually draws the main issue for the barrier of use of the biodegradable. But obviously, we know the benefit to the environment, sustainability, and so on. So hopefully that will drive and more uses, and probably will reduce the cost of this. So anyway, I just want to summarize at the end, and I probably took a little bit longer time. Did I use more time? Biopolymers, bio-based polymers are gaining interest, I think, in the packaging market. I'm outside of the package, but I just see based on the recent, I did some homework in the past week, and the PLA blends already get some more applications. The PHA, I think, my imagination on PHA would be very good, and because PHA has potential and to be mass produced, and also with a lot of potential. So still, the cost is the issue. So with that, I thanks for your attention. I will welcome any kind of questions. Thank you.
Thank you very much. I learned so much. I have a lot of questions too, and I'm sure other people do as well. And I'm really looking forward to digging into some of that in the discussion. We are a little over time, so I'm probably going to take one question right now, and I'm going to turn it to Rana to do that. And then we'll move on. But there, if you have a question, write it down, and please bring it up during the roundtable, which is coming up. Take one.
Thanks for the presentation. I just wanted to ask about PHAs, because actually there's been a huge, they were widely advertised, there was this, about 5 to 10 years ago, and they were kind of discovered, and there was this huge potential, but actually we haven't seen that scale up, and in the meantime we've seen PLA scale up. So yeah, I just wanted to ask what your thoughts on this, because I'm afraid that there's a bit too much hype, but we aren't seeing that being commercially developed, at least in food packaging applications.
I think I heard a similar story, because I was more working in the fiber making, and PLA is a good candidate and for fiber, and also PHA is one. And I do know that several huge producers for PHA, But one of the major issues I heard was the inconsistent properties of the PHA. That's the one major drawback. I don't know how do they control the quality, but they do. Everyone is hoping to get the good, properties, good performance. But if they could control, that would be. That's just one. And obviously there are many other researchers and at lab scale or pilot scale, but not at the mass production scale. But for mass production scale, I think the consistency of this quality is the issue.